What about manganese? So manganese, in terms of uptake in plants, manganese is mostly absorbed by plants as manganese plus 2, right? And so what's found in soils oftentimes? Well, oftentimes manganese plus 4 is found in soils. So manganese plus 2 is a reduced form of manganese, and manganese plus 4 is an oxidized form of manganese. And so manganese, when it's found in soils, it might be manganese oxide, and it needs to be reduced before being absorbed by the plant as manganese plus 2. Okay, so keep in mind that manganese plus 2 is absorbed by plants. Chelates from organic materials can aid in the uptake. So just like copper, chelates can grab a hold of manganese and carry manganese from an area of high concentration, say in the bulk soil, to an area of low concentration, say near the root. And so chelate manganese, carry it to the root, release manganese for root uptake, go back out. The chelate grabs more manganese, carries it to the root, and releases it. Eventually, the chelate is degraded because it's organic in nature. It has a lot of carbon present in it, so it's attacked by microorganisms and degraded. Letter D. Theoretically, manganese does not compete with copper and zinc uptake due to a specific transporter protein that crosses the plasma membrane of the root. And I can tell you that as of recent, this may not be true, or it may be true. And so letter D is take it with a grain of salt right now. Most people think it does not compete for uptake with copper and zinc, but in some instances, it looks like it does compete with copper and zinc uptake. So the jury is still out. I like the picture of rhodochrosite. This is a picture of manganese carbonate. This form of rhodochrosite or manganese carbonate was found in a mine in Colorado. It's about the size of maybe your fist. And if you ever go to the Denver Museum of Nature and Science, it's in the geology section, and it's really, really beautiful to look at. It's probably priceless, to be honest with you. The functions within plants. So manganese facilitates electron transport during photosynthesis, and it actually activates enzymes that lead to eventual storage of plant carbohydrates. So that's illustrated in this graph that you see in front of you. And on the x-axis, you have the plant part, either the root, stem, or leaf. And on the y-axis is soluble carbohydrates that are present either in the root, stem, or leaf. And under low versus adequate manganese concentrations in the soil, you can see the difference in the carbohydrates that are accumulated in the root or the stem or the leaf. They're drastically different in terms of concentrations. And this is simply a function of the ability of manganese to activate enzymes that trigger the ability of plants to store carbohydrates. So what does a deficiency look like? When we see a deficiency, we see, and this should say interveinal chlorosis. We see interveinal chlorosis on young leaves. So what does that mean in terms of mobility within plants? We find this in young leaves. Oh yeah, I just learned about this in the copper unit, which is in the same unit as this unit. So copper is in younger leaves. And so when a plant perceives a deficiency, it cannot scavenge manganese from older leaves. And so that tells you that manganese is not mobile within plants. All right, so the concentrations of manganese that are present in older leaves remains present in the older leaves, and the newer leaves suffer. I can tell you that the interveinal chlorosis looks a lot like an iron deficiency, and sometimes it is confusing to tell the difference between the two. So I'll share with you a picture on the next slide that shows you this confusion. When we see manganese deficiencies, it occurs at high pH, right? So here's a figure that you've seen before. And here is manganese. And as pH is on the x-axis on the very top of this figure. And as you move from left to right, from acidic to basic conditions, the availability of manganese decreases. Same thing happens with copper and zinc and iron. And so these micronutrients that we've been discussing in this class all decrease in terms of availability as pH increases. Manganese is no exception. And so deficiencies occur at high pH. Now, I can tell you that more often than not, because manganese does look like an iron deficiency, that if you're going to see a deficiency at high pH, you're likely going to see an iron deficiency over a manganese deficiency. However, if you're unsure, it is always best to pull soil samples and plant tissue samples and have them analyzed at a reliable laboratory to be certain. When manganese is deficient, we see reduced photosynthesis and we see reduced root and shoot growth as well. So let me share with you some pictures. And these are the pictures I want to share with you. So here's manganese in the top right-hand corner, or manganese deficiency in soybean. And you can see it's interveinal chlorosis. It may be hard to tell that it is found in newer leaves, but it is found in the newer leaves, or the leaves that are highest up in the plant. In corn, you see a manganese deficiency on the left-hand side. And for reference, you see the iron deficiency in the bottom right-hand corner. And they look almost identical. In fact, I think they look identical to my eye. And so to be certain whether or not it is an iron or a manganese deficiency, you really should pull plant tissue samples. And if you're curious, pull soil samples as well. So here's a table of the sensitivity of various crops to manganese. And the one I want to point out to you is soybean. And because manganese undergoes oxidation reduction much like iron, and remember from when you learned about iron and the sensitivity of crops, soybean crossed the high, medium, and low sensitivity boundary. Well, guess what? The same thing happens with manganese and soybean. Just FYI. So how do we overcome manganese deficiencies? We add manganese sources in the terms of organic materials or amendments or inorganic amendments. And the organic amendments that supply manganese, that supply adequate amounts of manganese, are manures or compost or biosolids. And these certainly all three supply enough manganese to supply or meet the needs of a crop, which is probably somewhere between 2 to, I'm guessing, 5 parts per million in the soil. It's pretty low. You can actually apply inorganic manganese fertilizers in the form of metal sulfates. So manganese sulfate contains 26% manganese. The 26% is not magic number. It comes from the amount of manganese in manganese sulfate that includes 4 waters. So it's all based on molecular weights of manganese to the molecular weight of manganese sulfate with 4 waters. This is a pretty common source. We can band apply it at 5 to 10 pounds of manganese per acre. If you broadcast it, you need to increase the application rate because manganese actually forms associations in soils and its availability is reduced when it forms associations with oxides, hydroxides, or carbonate phases. It can be foliar applied, and if you mine manganese sulfate and don't simply just crush it, you can apply it as an organic material. That's all you do. You can actually also apply manganese chelates, and these are usually foliar applied. And if they are applied, they cannot be used in organic systems because EDDHA and EDTA are man-made substances. And this brings us to the end of this unit.